Okay, so today we're going to talk a little bit about graphing and common graphing mistakes. So the first thing I want you to look at is the common graphing mistakes handout. Click on that and it comes up with an exemplary graph. What is so exemplary about this graph? Well,
Did you get that?
rather than looking at the exemplary graph first, let's look at the common mistakes first. Oh, sorry, the link? It's under Handout, Common Graphing Mistakes. If you refresh, you'll be able to see it. All right, back to common graphing mistakes. Take a look at the handout. It looks like this. Let's just look at the first one. What's wrong with the picture on the left?
Nothing. The numbers on the list.
What's wrong with the numbers?
They're in the middle of the boxes. They should be on the. There's like a 2 and then 2 boxes.
Yeah, it's really hard to tell if you look at it. You know, is that 4? Which line is that 4 on? Right. So common mistake to make. Another one. Right below that. So, what's wrong with this numbering here?
It's inconsistent.
Inconsistent means what?
It doesn't fit the same pattern.
Okay, so what do you mean by that? Give me a fix for it.
Number of units. There should be a space between the 0 and 2, just like all the other ones.
Okay, so it should either go 0, 2, 4, 6, 8, or there should be a space between the 0 and the 2. So you're counting up by 1. Okay, good. Next one. This one, well...
There's more points below it than there.
Yeah, it's a little sloppy. To me, it looks like that person picked these 4 data points and said, I like those 4 data points. I'm going to draw the line through them. Rather than thinking about what the best, rather than me just going into that, why don't I ask you this? What is a best fit line?
Has equal number of points on top. Well, what if
So you're saying that the reason we draw a best fit line is so we can find some line with an equal number of points above and below.
To get a general trend of what the.
Okay, who here thinks that the best fit line is an average? What were you saying?
Just to get like a general trend of what the information of the data is doing in real life.
I'm going to get a little philosophical here. Why would you draw a best fit line?
The ideal.
To be ideal. So, yeah, Justin, what do you think?
Draw a best fit line if you have a whole bunch of data points that don't seem to have a relation to each other.
So if you didn't have a whole bunch of data points, you wouldn't draw a best fit line if you only had a couple?
I only had a couple of them in that experiments.
Oh, really? Really?
Yes, I am.
Okay, what do you think,
If
Brandon?
you have a bunch of data points that you got from doing an experiment, there's always that slight error in the experiment. So, if you just tried to make a graph that all those lines that fit all those points, it wouldn't be any use.
You guys are missing it. What do you think?
by using a best fit line, it's easier to predict what.
Oh, now we're getting somewhere. What is the point of drawing a best fit line? Why would you draw a best fit line?
To predict.
Well, one of the major reasons is so we can predict. But what is a best fit line?
Has a slope.
It might have a slope of 0. But think about it this way. Let's say if this were a position versus time graph, and this was the position versus time graph for a car. And all you had was the data points, and you just left it at that. You never bothered drawing a best fit line. What would you effectively be saying that the car did?
Transported, like teleported.
It teleported, right. It teleported from this spot to that spot. to that spot, to that spot, to that spot, to that spot, to that spot. Is that what the car actually did when you watched it with your eyes?
Mine doesn't.
Yes, I have a teleporting car. No, what did the car do?
Move.
It moved smoothly, right?
Maybe not so smooth.
Well, maybe not so smoothly, but what a best fit line is your, as a thinking human being, your interpretation of what you think actually happened. Do you see why a best fit line is so important?
Yes.
You are the human who interprets the data. And the best fit line is your interpretation of truth. You got it? So if you had dot, 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 all nice and lined up, and you had one data point right here, would that mean that you draw a best fit line that goes like this? Here, let me actually draw one. Would that mean your best fit line goes like that?
That'd be awesome.
Yes or no?
No.
Of course not. Why not?
It went back in time.
Right, because then you'd be saying that the car went back in time and it occupied two positions simultaneously.
That would be so cool.
Right, if you're taking a quantum physics class, then maybe, but not so much in classical mechanics. All right, you guys get the picture? So, if you do have a data point that's up here somewhere, what are you going to do about it? Move your line over. Right. We're going to look at that and say, you know what, my best fit according to if I do like a least squares and regression analysis, my best fit should now look something more like that. That's what you do, right?
Yeah.
No! No! That's stupid! No, you don't do that. All your points are all nice and lined up in a nice line, and oh, you got one data point over there? Oh, I better move my line.
A little bit.
Do you?
That's what the computer would do.
Oh, that is what a computer would do. How smart are computers?
Computers are stupid.
They're
They
just
are
good at
very
following directions.
stupid. They are very stupid. And a computer will do that, but should you do that?
No,
No, why not?
because we're humans.
But I thought
Because what would it imply if you had a data point right there?
You missed it.
It's an outlier. It's an outlier. And if you've got an outlier, what should you do? If your lab was taking position versus time data of a car and you got one of your data points right there, what should you do? Probably retest. Unless there was some crazy physics going on that involved teleportation, chances are that data point is a boo-boo. Got it? You always have to think about any outlier and consider it carefully. And if you retest and you retest and you retest and that outlier is still there, guess what you're going to have to do to your model? Probably revise your model. There might be some crazy physics going on that you're not thinking about. But your first response should be, if you got an outlier, retest. Sound good? Do not simply do what they told you to do in math class and plug it into a linear regression and do some average. Because if you do that, you are completely negligent in your responsibilities as a thinking human being. All right? And I will crush you for it. Sound good?
A little bit scary, but sure.
All right. Do not blindly draw lines through data without thinking about it. Because remember, the whole point of the best fit line is what you think the truth is. Good? All right. Let's see. All right. If you go back up to the top here. So this is an example of a good graph, and it's got these data points. They're all plotted here. And then I drew a best fit line in red. And then what are these circles?
2 points.
2 points used to find the acceleration. Nicely done. Nicely done. To find the slope of the best fit line, right? What do you notice about point 2? It's not a data point. Nicely done. Nicely done. Should your data points lie on your best fit line? Yes or no?
Only coincidentally.
Only coincidentally. Nicely done. I like the way you said that. In fact, if you had a precision of like 15 digits in your measurement, should your best fit line go through any of those data points? Probably not. Does that make sense? Why not? Why shouldn't your best fit line go through any data points? Theoretically. Unless you have 2 data points. Yeah.
Because then it makes the data point it's going to more significant than the others.
I disagree. Yes.
Does any data that you have above and below change the fact that it's not going to be exactly perfect?
Oh, I like that exactly perfect statement. What is a best fit line again? Your interpretation of what? The truth of what actually happened. What is a data point?
What you measured.
What you measured. So did you measure what actually happened?
No.
What did you measure?
1 point in that.
You measured something, and your measurements are always have some error associated with them, right? Agree?
Yes.
Yeah.
So if you think about it, the best fit line is what you think truth is what you actually happened, and a data point that you take always has some error associated with it. Should your best fit line go through a data point? No, because best fit line is truth, and data points are approximation of truth. Does that make sense? All right. You should always, by definition, trust your best fit line because that's what you did, right? Or what you think the truth is. And always, by definition, know that there's some error associated with any data point. Good? All right. So, anyway, kind of a philosophical thing. But you need to understand that about best fit lines. They are not just some exercise in linear regression on your calculator. They are the most important thing that you put on your graph. It's your interpretation. Never fail. If you think there is a relationship there, never fail to write it down. Now, should best fit lines always be straight?
Yes.
Okay, so if you're plotting position versus time of a falling object,
No.
and the data points kind of made a parabola, right? So you put a straight line through that, right? No, of course not. What do you think happened?
It accelerated down.
Yeah, a parabola. So if you think it's a parabola, do it as a parabola. All right? And I think in chemistry class they said, oh, best fit lines are always straight. No, that's not true. Best fit line is whatever you think the model is. It just so happens that in chemistry class, a lot of the models were very simple and made straight lines. But in this class, not so much. Yeah, we're going to have all sorts of curvy things. Actually, we're only going to have a limited few, but you'll see them when you see them. All right, cool. What else? Last one. Other common mistakes. Forgetting to label the axis, no units. Numbers don't start at 0. Best fit slope calculated from points too close. Ooh. Common mistake is if you're going to calculate the slope of a best fit line, you pick a point here and a point there that are like
Too close.
Too close. Why does that throw you off? Why could that throw you off? Yeah.
Because you're not getting the slope over a long period of time, you're only taking a small segment.
Yeah. And you can introduce some error. Now, if your best fit line was done via linear regression on a computer, that shouldn't matter. But if you do it kind of graphically, that can matter a lot. So, all right. Let's see what else is on here. Oh, okay. Next one, percent error. Raise your hand if you know what percent error means. Okay. Now, in this class, we don't talk so much about percent error. We talk more about percent difference. What's the difference? What's the difference between the words percent error and the percent difference?
Not saying it wrong.
I like that. Yes, absolutely. Percent error implies that you did something wrong, or that you're deviating from something that is accepted, right? Percent difference just means you have one value and a different value, and there's a difference between the two. All right, there are actually 3 different ways to think about percent error, but they all come down to the same basic thing. We want to take the difference between two things, and the divide by whatever we trust most. Got it? All right, so first example. So difference between two things and divide by whatever we trust most. All right. So, everybody pull out your calculator, and we're going to do the first kind of percent difference calculation. And this is the one that you commonly refer to as percent error. All right, so let's say you are doing a lab that you will be doing here very soon. It's kind of a simple lab, and you take some measurements, and you calculate the acceleration due to gravity. You calculate it all out, and you get a value of 10.1 meters per second squared. What's your percent error? Go. In your lab, you find acceleration due to gravity is 10.1 meters per second squared. 10.1. Okay, so what was your experimental value? 10.1. And what's the accepted value? 9.8. Now, remember, it's the difference between the two divided by what do you trust most?
9.8.
9.8. So divided by 9.8. And so what do you get?
3.06.
What is it?
Wait.
3.06%? Okay, sound good? Everybody get that? All right, so that's the common way to do it. All right, now, or kind of the classical way. So there's another way to do it. And this actually, I think in AP Physics B, you did a lot of labs that basically did this. You measured something experimentally, and you calculated what the value should be according to theory, and then you compared the two. Which one do you trust most? Do you trust the theoretical one, or do you trust the experimental one more? Well, all right. So yeah, we are always comparing to what theory should be, right? So we do experimental minus theoretical divided by theoretical. Okay, last one, and this is my favorite one. Let's see. Suvi, how old are you?
17.
Natalia, how old are you?
7.
Okay. Is anyone in 16?
I don't think anyone's.
Anyone 18? Anyone 18?
Shift 16.
Okay, so Suvi and Shiv. All right, so what is the percent error between your ages?
Shiv, you're wrong for being 16.
You see the problem with that statement, right? You shouldn't be talking about percent error. What should you be talking about? Percent difference. Okay, so what's the percent difference between your ages? Go.
But who's right or
Oh,
wrong?
right. Who's more right? Is Suvi more right for being 17 or Shiv more right for being 16?
I'm gonna go with
1 over 7. 5.9% wrong.
What do? You go clearly you go 17 minus 16 on top,
Over 7. Oh,
but what do you put on bottom?
16.5.
I like 16.5. Does that make sense? If there is no value that you trust any more than any other value, then just average them and use that. Make sense? So 6% difference. Sound good? All right. So the reality is, just like best fit lines, the way you should be doing percent difference calculations is always a scientific judgment call. Now, some other scientists might not agree with you, and we might come to a consensus in how we want to do this, but it is a judgment call. All right? What do you trust most? All right? So whenever you're doing this in a lab, keep that in mind. Keep this sheet in mind, and it'll be in your on the website, so you can always refer back to it. All right, everybody got all that? Sound good? All right, so last little bit of today's lecture is sometimes we'll have a bunch of data, and that data might not be some nice, simple function. For example, you might have some data that looks like that. All right, and I might ask you, what's the total distance traveled for the first 800 seconds? What do you do? Yep, it's a velocity versus time graph, and we know that the area under the velocity versus time graph should give us the distance traveled, right? Or is it displacement? I can't remember. Boy, I think I made a mistake in this too. Do you guys see it? What's the mistake?
Displacement.
I did displacement, not distance. And the difference is, I took this area, which was 250, this area, which was 1,000, this area, which is 1,500, this area is 1,000, and I should have added it to that area, even though it's backward. Does that make sense? Oops. So what should the answer be?
3,750.
Wait, so you found distance now? Wait, no.
5,000, yeah.
5,250.
Dino's right.
Yeah, 5,250. Yeah, I found displacement, not distance. Oops. All right. Everybody got that?
Because if you add 1,500, it just cancels it out. You have to add it twice.
Yeah. Good? All right, so the answer should be 5,250 meters for distance, or 2,250 meters for displacement. All right, next one. So area under the curve, common way to do that, and I think you guys all know that. An average slope. Sometimes you might want to find the average slope between 2 points. What if you had something like that? And it's a velocity versus time graph, and I wanted you to figure out the average acceleration between, oh boy, between here and here. How would you do that? Or actually, sorry, between 50 milliseconds and 80 milliseconds. What would you do?
Try to see it.
Yeah, how do you do the secant line, though? Yeah.
It's just a straight line between the 2 points.
Yeah, you could go from here to here, and you say, well, figure out the slope of that thing. So it goes down 20, and it goes over 30 milliseconds, which is 0.03 seconds. So all being said, the average acceleration between here and here is about negative 6.66666, whatever, meters per second, 6.67. Sound good?
It's gonna be
All right. So a lot of times in real life, data is messy. And best fit lines are a way to deal with that. But also you just kind of have to look at something and go, "Ah, that looks like it's going down," which means I can calculate an average. Sound good? All right, I think that's it for the day. Oop. Yeah, that's it. Nice job, guys.